So let's talk about displacement, time, and average velocity. And I'll explain why we're talking about average and not regular velocity in a minute. So there's more Arrested Development jokes, but let's just talk about the difference between a regular, everyday definition and a physics definition. So if you looked up the definition of motion, there's lots of different ways. There's things like connotation, the context of what you're using the word in, all of that stuff. But this isn't an English class. What we talk about is the physics definition. And when we talk about motion, it has a very specific definition in physics. It's a change in position, right, where these underlined words actually have meanings as well, of an object with respect to time and its reference point. And what I mean by these things have definitions is they have mathematical definitions. So change means that you had one thing and now you have one number and now you have a different number. Okay. Position means you're going to have something like a coordinate system and you're going to have to plot something on that coordinate system that has a reference to a zero. Okay. Time is time, and then reference point would be your origin usually. Okay. So when you're reading physics problems, what you're looking for is how to translate the words into physics and math, okay? And once you get used to looking at problems that way, it makes them a lot easier to do. You're really just looking for keywords, and sometimes these words are explicit. We'll try to start out that way, but later they become sort of implied. Like you can assume, if something says, we want to know how far this thing goes, you're going to have to translate how far to like final position, okay? So starting to understand that. So it's a lot like learning a language in the fact that your brain takes a little bit to adjust and adapt to reading things that way. So that's the reason it's important to do a lot of problems and sort of do a little bit every day and let it sort of marinate in your head so that you can understand it instinctively and intuitively, okay? All right, so let's take a statement and translate it into physics, okay? So let's say that Carl Weathers is back, so upwards of 3 of you will get this joke, but it doesn't matter. Carl Weathers walked, and part of the reason I do this really obscure joke is because you don't have to understand any of that to do the problem, okay? So he's walking to craft services. Does anybody know what craft services is? Yeah, what is it?
It's the food services on set.
Yeah, so if you're filming a movie, they have catering for the movie and they call it craft services. I don't know why. There's probably some historical movie language reason for that, but if you're working on a movie set and you want snacks, you go to craft services. Okay, so Carl Weathers must be on a movie set. He's walking over to eat a crudité, okay, which means fresh vegetables. Okay, but we don't need to know any of that because all we need to know is this thing moved over to this thing, okay? So how do we describe this statement in physics, okay? And I'll post this later, but this is the scene from Arrested Development that joke is from, so in case you want to watch that later, you can. Okay, so how do we describe where Carl is?
Position.
On a graph, right? We need some sort of line, and then we also need to know where craft services is, so we'll have to also plot that on a line, okay? So first off, we make each of these things a point. So now this is the point that represents food, and this is the point that represents Carl. But we'll call them position A and position B because it doesn't actually matter that one of them is Carl and one of them is food. They're just 2 separate locations on a number line, okay? So this is called position. We rewrote those in math. So now we didn't even call them position A and position B. We say, okay, we can put this on the x-axis. We don't have to. We can put it on the y or the z-axis, but the x-axis is usually what we use for horizontal, so we're going to do that. So this is x sub A, so it's a subscript that means it's position A, and then this is x sub B, which means it's position B. And you can use any letters you want. If you wanted to call this, well, part of the reason I didn't use C is because they both started with C, but if you wanted to call this x sub C and x sub F for food, you could do that. Those are all perfectly reasonable, but often we just use A, B, C because it's easy, okay? We're just indexing things. And then we say with respect to, Well, that's a reference point, right? So that means we need a frame of reference. We need to put these things on your frame of reference. And you probably need to figure out what the origin is and what the units are. Okay? So we cut this thing up into, let's say, meters, and then we pick a 0. And the nice thing about setting up physics problems is you are in charge of everything. So you can design the problem to be easy to solve. And we'll talk about what that means later. But where you put 0 can usually make the problem easier or harder. And there's usually a pretty obvious place to put it. You probably want to put it either here or here. And since this is where he's starting, you can put it here. So we're going to say, okay, this is a reference point we call the origin. That's where Carl's starting. All right? And then this is the initial position. This is the final position. So if these are meters, we can number this now. And we've done this a little bit backwards, right? Usually positive is that way, but that's just something we choose, okay? So as long as we're okay with this, that's fine. It didn't say he was going a particular direction. We just drew it that way, okay? So here's our frame of reference. Now we can describe position. Position A is at 0 meters. Position B is at 7 meters, okay? So if we want to know how far he walked, what do? Yeah, we get the change in position, okay? And change is written as delta, okay? So delta always means change. So if you want to do change in position, that is delta x, which is x final minus x initial, okay? Let's say you want to know the change in velocity. You could say change in velocity, which is v final minus v initial. Let's say you want to know the change in anything. Well, you could say the change in pineapple is what? Final pineapple minus, sorry, I'm not good at drawing pineapples, and minus initial pineapple. So delta just means change in. It means final minus initial. Anytime you see delta, that's what it means in physics for the most part. If it's upside down, it's a different story. But if it's just a triangle, delta, okay? That is a change in something. So you write this out. Final position is B. Initial position is A in this case. So 7 minus 0, 7 meters. To the left. Why does it say to the left? It's now a vector, okay? This is a displacement vector. Okay, so we could put an arrow over it if we wanted to. So this change in position is known as displacement. Okay, and displacement, remember, is a little bit different from distance. Distance is the total amount traveled. Displacement is just described as the change in position, so final minus initial. So if I did some sort of weird walk over here, but I started there and ended up there, my displacement would just be this straight line part. Okay, even though my distance traveled would be much longer. So that's not because we don't care about the distance traveled in this case. It's just that's the definition. Okay. So when does he start walking? Let's say he starts walking at 0 seconds. Does he have to start walking at 0 seconds? No. Why might we want to choose 0? Yeah. But let's say you had a stopwatch and you were just watching it and you noticed he started walking at 2 seconds. You could call it 2 seconds. But the neat thing about differences when you use the change, usually values here are what we call invariant. So no matter what coordinate system we use, no matter when we start, whether we start at 0 or 2, the displacement or the time difference, the delta, should be the same. Okay? So that's why it's okay to pick an arbitrary coordinate system and pick a 0 where you want it, because the change is always going to be the same, and that's the thing that determines the answer usually. Okay? So when does he start walking? 0 seconds. When he gets there, you're at 35 seconds. Okay, so we know the time he's at position A, and we know the time he's at position B. So we call those TA and TB, and then we say, okay, 0 seconds, 35 seconds. All right, so this is called time. So if we ask how long does it take him to get there, well, that's delta T. So time final minus time initial. That's why it's nice to choose 0, right? Because subtracting 0 is easy. Yes?
Could we ever do that with distance? like say, oh, how long did you take instead of saying, oh, it took me 5 minutes. It's like, it took me 2 days.
Yeah, you could say that.
Okay.
But what I mean is, like, so for instance, if I say this is 0 and I walk 1 meter, okay, then my initial position is 0, my final position is 1, and my displacement is 1 meter. But I could also say 0 is way over there, I'm at 4 meters here. If I walk 1 meter and I'm at 5 meters, my initial and final position are different. Now it's 4 and 5, but my displacement is still 1, okay? So no matter how I set up my number line, it doesn't change the fact that I've walked 1 meter. So displacement is invariant. No matter what coordinate system you choose, no matter what units you choose, it should be able to match any other answer. Yeah. Okay. And this is why, and this is something that frustrates students, there are usually many ways to solve a physics problem. Some of them are easier and faster, but there's lots of different correct ways to solve any physics problem. It's just, how easy do you want your life to be? And it should work that way because what we're doing is just mapping math to physical stuff, okay? So things happening in the real world. And as long as your assumptions about what you're doing are sound and you build a good model, it should work. Yeah. Okay. So the other thing, next thing we want to do something a little bit trickier. So we want to know how fast is Carl going, and we're going to assume he's moving at a constant speed. I won't get into it now, but it's actually important for the definition, okay? So if we want to figure out how fast he's going, well, then we just divide our change in position by our time interval, right? Delta x over delta t, all right? Because we have distance and we have time, and we want to figure out distance per time. So that's the extra simple way of doing it. So we take 7 and we divide it by 35, and I picked these numbers on purpose because you can divide them nicely, right? This ends up being 1/5 because 7 divides nicely into 35, which is 0.2, okay? So we have 0.2 meters per second. You don't have to write seconds. You can just write m divided by s. I've just been writing it to get used to translating from words to stuff, okay? This is known as average speed. And to do average speed, we just put this little line over it. It is not the definition of velocity, okay? It's close, and in this case, it'll be the same thing, but it's not the same, okay? If we add a direction, now it's velocity, right? Speed is just the number, but if we say he's going 0.2 meters per second to the left, or any kind of directional indicator, that means we have velocity, okay? So here's all the stuff that we've gone over already. We have position, that's just where an object is on a coordinate system. We have displacement, that's the difference between two positions. We have time, that's just when an object is in a particular place. We have time interval, which is the difference between two times. We have speed, which is how fast an object moves. And we have velocity, which is how fast an object moves in a specific direction, so as a vector, okay? It's not super necessary at this point to call things vectors because we're only working in one dimension. As we add 2 and 3 dimensions, the vector part becomes like really crucial, okay? So if we say Carl walked 3 meters, will we still know where he is? Yeah, what are the possibilities here? Yeah, he could be over here. Let's see. Oh, I've lost it. There it goes. So he could be over here. He could be over here. So we don't really know, okay? And that's why vectors, and even in one dimension, sometimes are important, because in this case, 3 meters, that's a scalar quantity, but it doesn't tell us, I mean, he could also have walked this way or that way or up or down, like we just know he's moved 3 meters, so that could be in any direction. If we give the direction, now it's a much more specific mapping. So this is part of the reason vectors are pretty important. So if we want to write this, if we say like, okay, he walked 3 meters to the right, that means we know he went this way, okay? And we can write this as delta x, that's the displacement. Here's an arrow that says it's a vector. So we have 3 meters, but we also have to include this unit vector to give us the direction. So you could call this x hat or I hat, as it just means in the positive x direction, okay? A vector of length 1 in the positive x direction. Remember, scalar vector multiplication means this is now a vector of length 3 in the positive x direction. Okay, so remember, a vector is a physical quantity with both magnitude and direction, so now we know specifically where he is. Oh, yes. All right, so this brings us to our first clicker question. So we've got some A, some B, and some C. So please talk to the people around you, or in the chat you can discuss with other people in the chat and explain your answer. Oops. And we'll vote again. And we must say, oh, it's like a nice curve. So the answer is going to be C. Okay, somehow. Cool. Well, I've somehow lost the answer. But the answer is going to be C. And this is the difference between displacement and distance. Okay, so remember, it's it's asking for average velocity versus average speed. So the average speed is going to be distance over time, right? So at each point, what speed are you going, and you average them all together. The average velocity is defined as final position minus initial position divided by total time. So for instance, if I walk this way, and I walk all the way back to the point I started, let's say I walked 3 meters, okay, total, but my initial and final position are 0. So what's my average velocity? 0. But my average speed is obviously going to be 3 meters divided by however much time it took me to do that. But the average velocity is 0. So because of the way these things are defined, they tell us different things about our object. Okay? The average speed tells us at each point how fast was I going. The average velocity tells us how much happened over the course of the time. Okay? The other thing, if you added up, the other thing about average velocity is even if you added up all the different velocities, why would it still be 0? Well, all of these, when I'm walking this way, they all point this way. If I walk the same velocity back, they all point this way. So even if you add them up and I'm going 1 meter per second the whole time, it's 1 meter per second this way plus 1 meter per second that way, and they still cancel. Okay, so my average speed is more like the absolute value of my speed at each point, whereas the average velocity includes all of the directions. Okay, cool. So let's talk about displacement. So if we want to represent this as a vector, we can represent displacement as a displacement vector. So the magnitude would be the length of the vector. Remember this guy? And then the direction is just where the arrow points. So we already talked about this in the first chapter, but of course, now we want to add some of our definitions. So here's our initial position, here's our final position. And this is our total distance traveled, which remember is different from our displacement because our displacement is just the vector pointing from the initial to the final. Okay? So the displacement vector is drawn from the initial to final position regardless of the path followed, which is by definition. Okay? If we want to describe velocity as a vector, let's say we have our Roomba and it's speeding up. Okay? So let's say we take snapshots each time at each 1 second interval. All right, and you can think of that motion as smooth. I just paused it for every time that every time that we took a snapshot. So 0 seconds we're here, at 1 second we're here, at 2 seconds we're here. What do you notice about the distances? Yeah, they're getting bigger, right? So we have displacement vectors. Right, these are the instantaneous displacement vectors. So at each second, this is the displacement between 2 seconds, okay? If we want to draw our velocity vectors, they actually look surprisingly similar. Because remember, it's displacement divided by time. But what's the time? 1 second. So if you divide these vectors by 1, they look the same, okay? So that's the reason they look identical. Our total displacement looks like this, right? Our average velocity, what's that going to look like? Is it going to be this long? No, because that means you're going faster than all of these things. So what you do is you look at all the lengths of these vectors and you find the average. So the average velocity looks like this, okay? And that's the total displacement over the total time. Okay, so let's try another clicker question. I'll turn this on. So we're mostly thinking D. There's a few other answers. Please discuss and we'll vote again. Okay. Well, we're back to E. And these are both decent answers. So a particle moves from position 1 to position 2. So which way is the direction of motion? Down. So that means our velocity vector has to be down because that's the way it's actually moving. It's something going like this. So the velocity vector that makes the most sense is the one that points down. Okay? Cool. So, all right. So if we just go back to our original math, right? Position, not a vector. Displacement, vector. Okay? It's a change in position, and that has a direction associated with it. Time's not a vector. Speed's not a vector, but velocity is. So if you include a direction, you're doing a vector. Okay? The sign conventions, the standard ones, you don't have to use these ones, and we'll talk about that in more detail later. But unless you really need to, basically, it's the standard stuff. So if you're to the right of the origin, you're positive, left is negative, up is positive, down is negative. Okay? If you want to define these things, position is a location on an axis. A displacement vector is any magnitude and direction from that initial position. So here's our initial position, that's the green dot. Here's our final position, that's the red dot. The displacement vector is the arrow connecting them. Velocity vectors, right? The velocity vector includes both speed and direction. The speed is just the magnitude of the velocity, so if you took the absolute value of it, right? The average velocity is delta S over delta T. The instantaneous velocity, this is the definition. You could we could put an extra equal sign there to say definition. It's the derivative of the position with respect to time. So that's for each, because that's calculus, that's for each little piece, each little moment in time, an infinitesimal, little tiny chunk of time. You just take the little tiny distance you traveled divided by the little tiny time, and that gives you your velocity at that point. Yes?
Is there why is there the line on the S? It's not
The line on
the arrow.
So this S is a displacement, right? It's a displacement vector. It's complicated. It's not quite displacement, it's position, right? But it is a vector because you're looking at sort of a little tiny chunk. So it's kind of like, so because of this D, the sort of nomenclature of calculus and math is that delta is a D, right? If you're talking about Greek. So it's a big D. So big D delta is a displacement. This is a little tiny displacement. So because it's a D, this is like delta S. Okay, and there's actually, it's a fun math fact. Delta kind of means a big chunk. Okay, this is a little chunk, and a really tiny chunk is lowercase delta, and these sometimes get interchangeable. Okay, but you can put, pineapple on anything like this. But so yeah, if you're on like the x-axis, this is a little tiny piece of x, this is a big piece of x, and this is a little tiny piece of x that's probably smaller than this, but it's a fluid definition, okay? And then if you want to get real fancy, there's also this, which is called del, and that's a partial derivative of pineapple, okay? And that's when you get into multivariable calculus and like multivariable differential equations. So that's when you start doing partial differential equations. So I don't think any of you will get anywhere past ordinary, like just regular differential equations until upper division classes, okay? And some of you will never have to know about that at all. But if you're like in some sort of physics or engineering, there's a good chance you'll have to know about partial derivatives at some point. Okay, because that's what happens when we have more than one variable, right? If we only have x and t, simple. We don't really need that much in terms of, we can use differential equations, but we don't need to use partial derivatives or multiple integrals. But even in Calc 3, you'll start doing like double and triple integrals because you have to integrate over different variables if you have a 2 or 3 dimensional object. Anyway, okay.